Okay, so we can start today's session. Yeah, before that, we'll revise some concept about the working states method and also the limit state method. So, in the limit state method, the major difference is that the maximum strain in the tension of a reinforcement in the section at a failure shall not be less than this value, as you can see it here, Fy by 1.15 ES plus 0.02. Why is that so? Can anybody explain why is it not less than that? Here. Okay, we'll see on the line the why this is the least minimum. It should be more than that, and then only it's good to go for the design. So as we know that the yield stress we calculate by considering the slope at 0.02% strain, and then when it is cutting the stress strain graph, then that point is called as the yield strength of that steel. As we know that in the mild steel there is a definite yield point, but in the new steel like HYSD steel there is no definite yield point. So that's why this method is adapted to find the yield strength of the concrete. And then when we divide it by 1.15, we'll get the characteristic strength or the design strength. We will we'll get the design strength for to design the structures, which is similarly into the concrete. It is FCK, where it is FCK is called as the characteristic strength of the concrete, which is the 95, having the 95% probability of not exceeding that limit. When we take that and when we divide it by factor of safety, we'll get a 0.67 FCK. Sorry, FCK is the I will repeat, FCK is the ultimate strength, and 0.65 FCK is the characteristic strength of that material. And when we divide that by factor of safety, we'll get the 0.0 FCK divided by MIM, which is like around 0.45. Okay, so as you can see that for the concrete we have a lot of high factor of safeties. As you can see it here, for the steel we divided by 1.15, but for the steel concrete we divided by 1.5. That we already discussed in the last class. Because of the heterogeneity of the concrete material, we have the higher factor of safety for the concrete. Okay, yeah. So the limit state of collapse in a flexure single reinforcement section, as you can see, we can consider that the rectangular section with the AST is the area of a steel reinforcement having the total depth as a D, and the clear depth, like the effective depth, is a small d, which is not having the cover. Okay, we are not considering cover. The width is B. So this is called as depth of neutral axis. This is the strain envelope, where it is always assumed that the concrete will reach the maximum strain of 0.0035. This is already given in the IS codes. We have to consider that only. And the strain in the steel should be always greater than Fy by 1.15 ES plus 0.002. Okay, this value it should be always greater than that. Always greater than that. Now the stress envelope also we can draw, which will be, it can be any shape. It can be parabolic, rectangular, and trapezoidal also, but it should give the same result as per the as the experiment is giving. So here we generally use the parabolic one, as we know that when we divide characteristic strength of the concrete by factor of safety, which is 0.67 FCK. Sorry, I'm not able to write it here. Divided by 1.5 Yeah, so then you'll get 0.45, as you can see it here. And for the steel it is 0.87 Fy. So, so the tensile force is given by 0.87 Fy AST, and the compressive force we have to calculate. For that, we'll consider parabolic stress envelope. For that, to calculation of that, we'll use some method. In this, as you can see it here, at this location the force will be applicable. So this is 0.035, so, and this will be 0.02. By that we'll get this is a 0.57 and the remaining one will be here. Okay, so total compressive forces will be the total area minus this dashed area, right? So the first area will be 0.45 FCK, which is this value into depth. Okay, that is we have calculated here, and minus this, having the area of outer parabola can be calculated as a 1/3. It's approximate calculation. So 1/3 0.45 FCK into this value. This is 0.7 x. So that is we have put it, and then we have calculated the equation to calculate the compressive forces when the beam is loaded with the forces. So now you can see it is 0.364 FCK XUB, which is we can mention as a K1 FCK XUB. So now, can you tell me that on what this K value will be depend on? This K value, on what it will be depend on? Okay, consider it like if K1 is changing, means the position of C will change, and the lever arm, what is there, like this lever arm will also change. Now to change the lever arm, what we can think of how to change the lever arm, like how the lever arm will be changed inside the section. Okay, so the value of K is majorly this depend upon steel grade. So as the steel grade will change, the K values also will be changed. The K value we can also see in the upcoming slides, and you can remember that for the solving the problem quickly. So for the under reinforcement section, FST as we can consider as a 0.75 FCK. So XU by D, we always required it, will be equal to 0.87 Fy AST divided by 0.36 FCK BD. This is very much required. By that, we can say that our section is under reinforced, over reinforced, or balanced. Also, the XU by D can be calculated by the ratio of strains, which is equal to the strain in a concrete plus strain in a steel and strain in the concrete. So this is the formula. This is the formula to calculate the XU by D. So yes, also the XU by D for the different steel it is given, which is 0.53, 0.48 and 0.46. It is better to remember these values to solve the questions. And also the yield strain. Yield strain also you can remember directly to solve quickly. So this is like yield strain is like, if you don't remember, you can use this formula to calculate. By there you have to put the value of Fy here. For let's say Fe250, it will be 250, and Fe415, it will be 415, and then you can calculate it here. Or directly you can remember this. At least you can remember this. Also, professor told that it will be better to remember this value, so it will be easy to calculate. So expression for the resistance of movement for a balanced section in terms of Fy and the percentage of the steel we'll see now. As we know that the XU by D formula is this one. Okay, so Mu can be calculated as 0.7 by FCK AST, which is the tensile force into lever arm, or it may be compressive force into the lever arm. So we'll see the first by this way. So the lever arm you can calculate it is by D minus 0.146 XU, that 0.14 XU, 0.416 you can consider as a 0.42 for the approximation and to remember. And yes, then so then 0.42 you can consider there, and by putting the XU value here, the lever arm, the equations become this, and the lever arm equation, if you put into the Mu, this is the equation for Mu, is equal to 0.87 Fy ASTD into bracket 1 minus Fy AST divided by FCK BD. Okay, so this is the equation to calculate the moment of resistance. And as we said that the moment of resistance should be always greater than the bending moment of coming onto the any sections. So yes, so the expression for the resistance moment in the terms of concrete strain, for now we have considered this is as for the steel one. Now this is for the concrete. The only the earlier equation will change, which is the compressive forces 0.36 FCK XUB, which is the C, this is C, and this value 0.87 FCK AST, which is a T value. So if you remember it, it's like T into lever arm and C into lever arm. Same like working stress we have seen in the working stress method. As I said that 0.416 can be approximated to the 0.42, that is written here, and by solving this we'll get the equation like this, which is can be approximated by K into FCK into BD. Here also it is a K value. Okay, so which is this K value is given in the annexure G of IS 456 2000, which is again depend upon the steel grade of steel. This K values depend on the grade of steel. Okay, so for example they have calculated for Fe415. Okay, XU by DF for Fe415, we know that 0.48. Just 5 minutes back I told we have to remember this value, the middle one 0.42, right? That if you remember it, then we'll directly say XU by D is 0.48. For Mu, we'll directly put the XU by D value and we'll calculate Mu, which is 0.138 FCK BD square. This is for 415. As I said, this is the value of K, which is depend upon the steel grade, right? Okay. So the expression for the XU by D given the B, D and MU, if these values are given, then MU can be calculated by this. Okay. Then the lever arm is obviously calculated by D into bracket 1 minus 0.42 XU by D, as already we discussed. And if the stresses in the steel in FST a value less than the yield stress, then it is like 0.3 FCK XU by D BD is equal to FCK AST. Okay. And this also we have seen here. Okay. So calculation of steel area, also we have given B, D, MU, FCK, FY is given, then XU by compute XU by D, that we can do by the, we can do it by this table. This table is helpful always to calculate XU by D. Okay. Then MU, we know the formula for the MU, and the Z also we know, and the AST we can directly calculate by dividing 0.87 Fy into Z. So as I said, if you take this 0.87 Fy here and into AST, it's like a T, this value, and AST if you multiply by here, let's say 0.85 if you take at the left hand side, so it's like T. So T into lever arm is always will give you MU. So AST calculation is like this. So by dividing the 0.87 and then Z is the lever arm, we'll get the AST, which is the area of the steel. For that we have to always check that XU by D is less than XU by D, which is balance one, and it should be less than that, which means under reinforced section. Okay. So analysis and design of RC sections, like due to the concrete failure, the formula is this, as we already seen, and the K value can be calculated by this formula, which if you know this formula, then you can directly calculate. But directly you can remember these values, this, as this is given in the table, previously table we have seen. So directly you can put the K values and calculate the moment of resistance. Okay. So the second is like from the assumption that the steel reached the yield at failure. So for that, from the assumption that the steel reached yield at the failure, the formula is 0.87 Fy AST D into 1 bracket 1 minus AST Fy by BD FCK. Okay. Yeah. So it's also given here. And extra G is 456,000, which can also be written in the percentage of the steel formula. If the percentage of steel directly has given and they have said that calculate the moment of resistance, then we can use this formula, because this is the percentage of steel. P you can say the percentage of steel. Fy yield strength of the steel. FCK characteristic strength of the concrete. B width of the section. D is the depth of the section. Yeah. Okay then. So given MU, FCK, B and D. So for that also this equation we can use to find the XU by D. We already learn about that, how to calculate XU by D here. Okay, it should not exceeding the limiting value, as I said, as I also said it here. Okay, then for the balance section, the percentage limiting can be directly calculated as by this formula. Okay, and the lever arm is like this. This is expanded because XU by D we know that, which is FCK ST 0.0.3 FCK VD, which is also expanded here. Okay, so these are the different formulas we will use to solve the questions. Okay, we'll see the problem now and try to understand from that, and also I will give one question to solve you, and then you can try to solve. For that, if you want any formula to display, I will display that formula. You can use that formula and try to solve, but try to solve by yourself. For now, we'll see this problem. In that problem, it is given in the lecture also by Professor here, Dan, and he has calculated that. Calculate the ultimate moment carrying capacity of the rectangle beam. So these are the different parameters has given. Yeah. Okay. So see it here. B is given, total D is given, and the steel is given. Like everyone knows that what is the difference between this symbol and this symbol? Anybody? Like this symbol is like something like this, right?
It's for Thursday.
Yes. So this symbol is for the TMT or the QST we can say, and only phi symbol is for the mild steel. Okay, good one. The concrete strength is also given like M12T. Steel is also given as Fe415. So there is always good practice to start with the drawing the figure. We'll always draw the figure first to understand the question. So try to understand now. The rectangle we have to draw. Okay, the depth is already given 400, width is given 250. 3 bars is given, that is given in the question, and that is 16 mm dia, that also we have drawn. So as we know that this values no need to explain, like this value you have to by heart. The ES modulus of elasticity of steel, FCK is already given, Fy is also given. So strain you can calculate the limiting strain 0.87 Fy ES plus 0.02, so that becomes 0.0038. that I already told. For Fe415 by heart, remember it, it's here. Mostly the questions will be asked in the Fe415, so directly you can remember this 0.0038, and if someone is having problem in remembering, they can by directly solve by this equation they can use and directly get it. So the XU by D we can calculate. For that I told there is a formula to calculate XU by D at the starting. This is the formula, right? Where this is a strain in the concrete, this is a strain in a concrete again, and plus strain in a steel. They have used that, as you can see it here, they have used here to calculate approximation 0.48, right? So by now you should understand that when the modulus are like this strain, limiting strain in the steel is 0.0038, our XU by D is coming at 0.48, which is also we have seen it here. I am again showing this table so that you guys will remember that. Okay, Yeah, so they have calculated this, and for the ballast percentage of the steel, directly we can use this formula. Okay, 0.8, this AST they have written as a P by 100 into BD. Okay, and then P, rearranging this thing, the P by Fy by FCK can be calculated. Every value is given directly. PT, like percentage of steel, can be calculated. Here we have seen the formula for percentage of steel, right? But here it is related to EMU. So here we don't have, they have not given EMU. So for the balance one, this one, directly this formula you can use, right? 41 by 3 FCK by Fy XU by D. XU by D we have calculated first step here. This XU by D you can put it here, and this 41.4 directly you can use and calculate directly the PT. Why we are calculating that? Just to know that our section is under reinforced, over reinforced, or balance. So this is the PT calculator for the balance one. Now we'll calculate what is given. So area of steel provided is that the 3 bars they have provided with the 16 mm dia. So total is 603 mm. Total depth is B is 250, but depth is not 400, right? As you can see it here, you will be confused that you will take 400 here. We should not take 400. It is always effective depth. So it should be minus cover minus, what is this? Can anybody tell what is this? 16 by 2. And why we are taking like that?
Half of the diastole.
Yeah, half of the diastole. So by doing this, what we are doing? Which depth we are considering?
It's starting from half of steel to the top.
Yeah, center of the steel bar.
Yeah, center of diameter.
Yeah, center of the steel bar to the extremis fiber into the compression zone, right? Why we are doing that? Why we are not considering this section? Anybody? Why we are not considering the section? Oh, not even that. We are not even considering like half, like that, till that level only we are considering. Anybody? Why we are not considering the section of the beam which is like cover, as you can say, the cover of the beam we are not considering in our analysis?
Because steel will be taking all the tensile loads.
Yes.
Coming on it.
Yes. Correct answer. So it is assumed in the initial stages, we have assumed that all the tensile stresses is taken by the steel. So that's why we will neglect this concrete. Very good. So now we have calculated the effective depth, and then we'll calculate the percentage of the steel we have provided with. Just a minute. Okay. Then our percentage is coming 0.657 percentage, and by balance section it is coming at 0.957. So which is our given provided is less than balance one. So what which type of section will be this one? Our area percentage is less than the balance one, percentage area of the steel. Which type of section it will be?
Under reinforced.
Yeah, it will be under reinforced. If it is more than that, it will be over reinforced. If it is equal, then it's a balanced section. Okay. Then so calculate mu, and by having the percentage of steel, there is a direct formula. We already have seen that before this problem, and all the values we have now, like we have D, we have B, we have Fy, we have FCK, we have percentage of steel in our section, which is 0.657, not 0.9, because that is for the balance one, and Fy, everything we have calculated the moment of resistance. Okay, now we'll calculate by using the concrete failure. Okay, for the concrete failure, we also know that there is a formula, is mu 0.36 FCK BD square, XU by D in bracket 1 minus 0.42 XU by D. This becomes what? K into FCK BD square, right? FCK BD square, as we already say that, and with this K value we can calculate it. Okay, by this formula you can directly put all the values. We know X, we know XU by D, we know B, we know D, we know FCK, everything we know, we'll calculate it. So it is 93.13. So ultimate moment capacity is 68.98 kilonewton due to the steel failure. Okay, so here you can see that due to the concrete failure it is 93, and due to steel failure it is a 68.9. Is this design is good? Good means, is this design is optimum, or what should we do to make it optimum? Do you understand my question, or shall I explain it more? Like our moment of resistance, if we calculate during the concrete failure, it is 93.13 kilonewton per meter, and moment of resistance due to the steel failure is 68.98 kilonewton meter. So this value are not same. Is this good, or we can do it, like we can do more in these things? Everyone is following the lectures of professors. Like you have to follow the lectures, because this is like a revision thing. You'll not understand this quickly. So please always watch the videos of professor and then try to come for the live session of by PMRF. Here we'll see some problems you guys having for the solving, and also some problems we'll take, but you have to watch the videos, then only you'll understand all the theory behind it. Okay, so I will explain you. So there are these two different values. For the solving the question, it is okay, we got the answers, our work is done. But in the real practice, when we go to the like for use, in real case you are designing some beam or some slab, anything, this mu by concrete failure and the steel failure should be very close to each other. Like there should not be a major difference between them. Then it is like a optimum design for the steel, for that section. So both this value should be near to each other, then only we can say it is an optimum design. So how can we do that? Then we have to change this. Then we have to change this diameter, number of bars. We can take 4 bars and 12 dia, right? Four bars we can take, 12 dia we can take. Such a permutation and combination we have to do, and we have to come up with the solution where we have the mu calculated by concrete failure and the mu calculated by the steel failure are near to each other. So earlier it was very tedious process to calculate each and repetition time, but now there are softwares, they can do it in a seconds. Like these calculations. Okay. Okay, then again we'll brush up some basics, and then we'll see the one problem. Please try to solve that problem, so you'll understand everything. Like, okay, the failure is based on the principal strain theory. Yeah, this has to be we'll consider a principal strain theory as a failure, and the safety is checked to the ultimate load while the serviceability is checked to the service load. Why is that so? Safety is checked for the ultimate load while the serviceability is checked for the working load. Why is that? Obviously, the safety is more important than the serviceability. Serviceability is also important, but safety is more than serviceability. So it is always checked for the ultimate load. So in that way, we are saying that we are conservatively checking it. Okay, because we are checking it for very high load. Ultimate load is very high load, no, and the service load is the lower load. So safety should be checked for the ultimate load, which is the greater loads, and the serviceability should be. What is serviceability? We have discussed that. If it is safe also, but it is not serviceable, people will not like to stay there. For example, there is a lot of deflection in your structure, then people will not like to stay in that structure. So yes, so that is always checked for the service and working loads. So limit state method gives us smaller section dimension while more amount of reinforcements as compared to working stress method. Obviously we are optimizing the section, so the section given by the LSM will be smaller and slender. LSM is economical than WSM, as we also discussed in the previous class. Why is that so? Desired load in the LSM is ultimate load, characteristic load into factor of safety, while in a WSM, characteristic load is taken as a design load. Okay, and in a WSM, no factor of safety is designed for the load calculation, only factor of safety is for the design strength. In LSM, factor of safety used for the both design load and design strength, right? As we see, for the FCK also we are dividing it by 1.5, and for the load combination also we are multiplying by 1.5 the given load into 1.5 is like working load. So in the both way we are used in a LSM. Yeah, then it's again same thing for design of single reinforcement rectangle section. XU can be calculated by this way, that is we already seen. And then there will be 3 sections: balance section, under reinforced and over reinforced, that you can calculate by calculating XU. XU is for the balanced one, the limiting one, and your X. So if X is less than XU, then it's under reinforced. If it is greater than that, XU, if X is greater than XU, then it's over reinforced. If X is equal to XU, it's balanced section. So here it's also we have seen that this strain should be not less than 0.002 plus 0.87 Fy by ES, and this also we have seen. This is again the same thing. Okay. Yeah, for the over reinforced section we generally not prefer that, because section always fails in the crushing of the concrete and steel never fails, fractures, it always yields. So at the starting of the lecture I have asked that we consider the characteristic strength of the concrete for the design, but for the steel we consider the yield strength, right? Why is that so? Why not the ultimate strength for the steel and like ultimate strength for the concrete also? We consider ultimate strength for the concrete also only, and then we take the characteristic strength by that, and then we divide by partial factor of safety. Why is that so? Why steel is considered yield strength, and for the concrete it is characteristic strength? What will happen if we consider the ultimate load, ultimate strength of the steel as a design strength? Like here Fy we always says, no, what if we consider Fu? What will happen? Okay. Anyone know the answer? Why we consider? Here you can see that this is FCK and this is Fy. Why is that? Why there is no Fu? Like FCK is like ultimate here, considered as a ultimate of the concrete, and Fy is just yield strength. Why that is not like this? Will again it will go like this, no? Like this, not like this. It will go. Sorry, in the this type of steel it will directly. This is not mild steel, no, so it will directly go like this. Okay, so this will be maybe the ultimate load, and then it will fall down. And at this level, like this thing we have done 0.002 we have considered, and this becomes Fy, but we are taking Fy and not Fuy. Okay, I will explain you. See, the strength in a steel is very high compared to strain in a concrete. You can say that for the Fe415 it was about 0.038, right? Remember, that is only for Fy. If you consider that for the ultimate load, which will be even more than 0.0038, so the steel will go a lot of high strain, like it will deform, and in that deformation this concrete will not take that much strain and it will fail. Okay, so it is no use, like if you design your structure by using Fy, it will eventually fail at Fu. If you design your structure by Fu, it will eventually fail at Fy only, because the concrete can't take that much strain, right? So that's why we design it for Fy. Okay, but let's say because this RCC is like a composite structure, right? Both should have the similar strain or moreover similar. If someone is having higher strain than the other, then there will be stresses developed in them, and they whoever is the weaker will fail. So that's why the Fy of the steel is considered for the design and not the ultimate. Okay, we have seen this also we have seen. So under section, tension failure, ductile failure, very good. Like secondary compression failure also it is called as. Why it is called as secondary compression failure? It is called as ductile failure because failure is triggered by yielding of section. Okay, means you can see if the one beam is under-reinforcedly designed, you can see there are deflections and there will be the lot of deformation in the steel, but at the end the section will fail because of a crushing of a concrete only. That's why it is called as secondary compression failure. Okay, because after, let's say, steel reached Fy, then also we are again loading it. As I said that the steel will again deform. It will try to reach Fy. Before reaching Fy, the ultimate load in the steel will be reached and it will fail down. Okay? So that's why it is called as the secondary compression failure. Ore reinforced section is not recommended brittle failure, primary compression failure, because initial collapse is due to crushing of concrete. Okay, so it's not good. Why it is not good? Because concrete fails suddenly due to crushing before yielding, and you will not get any sign. Your beam will directly collapse and is hazardous for the safety of the people. So we'll try to solve these questions, and then for today we can wind up. Okay, so in this question, the design of a beam by LSN, maximum strain is limited to 0.0025. This is a change, you can see, right? What is limiting strain in actual limit set design? Anybody? You guys have to remember this. Okay, it is 0.0035, right? Everywhere it is given. See it here, 0.0035. Okay, or maybe I will show you the bigger image. See it here. This is assumed by a lot of trials, a lot of experiment. This is always assumed that the strain should not be more than 0.0035. Why is that so? Because if the strain is more than that, concrete will fail. Okay, so now there is a little bit change in that. Question is saying try to assume this as a ultimate strain is 0.0025. B is given, D is given, AST is given, Fe250, M30. Compute position of neutral axis for the balance section, and at a limit state of collapse of the flexure, calculate the forces on a compression zone of the section. That means we have to calculate C. What is C and what is X? Okay. Yeah, so I will wait for some time to you guys to attempt, and then we'll see the answer. So for that I will help you. This block diagram you can use. Okay, now this will change. No, this will become 0.0025. Other things you may assume as the same thing and try to solve. Okay, we'll wait for some minutes. If anybody wants another formula, then just tell me that. I will display that slide, so it will be helpful for you to solve. Okay, one more thing. This 0.57 and 1 minus 0.57, which will be that this value. Just a minute. this value 0.57 and this thing, this value. So it is calculated by trigonometry, by similarity of triangles. So you can use that. Only the change is that this will become 0.0025. So 0.0025 divided by 0.0025. So then this value 0.57 will change. Then you have to just put it here and then make an equation to calculate the compression forces. I will give you 4 minutes more and then we'll try to solve together. Okay, we'll see now. Anybody? Any answers? Okay. As you can see it here, as I said that the only 0.35 will change, other things will be remain same. That is 0. This is calculated by the strain in the steel. This is all everything we have put, and then XU is calculated. XU limiting is calculated, right? Any doubt in this? Yeah. Then as this formula will change, I said 0.25 and divided by 0.02, which will become XU limiting by AB. So there it was 0.57 and the 1 minus 0.57. Now that is changed to 0.8 here and 0.2, right? And these things we have put it into the formula of C. Everywhere you can see it 0.25 XU, 0.8 XU. We have put it that, and then we have calculated the formula for this is like 0.33 FCK XUV. What was the formula for the normal one? Anybody? By considering 0.0035, what will be the formula for C? C is equal to K into FCK BD. What was that? Here 0.364. Okay, so it's just a little bit change. 0.364 becomes 0.33 here. So C is equal to T. Will compare them. We have written that C is equal to T, and then we have put all the value. Then we have calculated XU. So XU is less than XU limiting. XU limiting we have calculated by this. Okay, right? Now that's because of that it's under enforced section. That was the first question asked, position of the neutral acting from the ballast section. So it's like under enforced. And the C we can calculate by 0.33 FCK XUB. XU we have calculated by putting that value. We'll get the C. Okay. Any doubt in this for understanding? Everyone understand? Raise the hand if you guys understand it. Yes, Varun. So it was just a small trick. They have changed the strain envelope. By that the stress envelope will change and the formula will somewhat change. And by that you have to solve the questions and get the values what they have asked. Okay, always remember this thing. For XU limiting, how to calculate. This is by similarity of triangles. Okay, consider this value is at the denominator, so which is like 0.0025 divided by this whole value, which will be equal to XU divided by D minus XU here. So always remember that. Maybe I can show you the normal formula. Yeah, this one. XU by D. This one is also fine to remember. Okay, any questions, like general questions, or maybe anything to be added? Okay, then I will see you guys on the next Monday. Probably I will not be available on that day. So if I am not available, try to join the TA session by the different PMRF students also. That will be conducted on Saturday and Sunday. If you guys are lucky to have the same content whatever you are attempting on the online, so that will help you, or you can be in touch with me, you can mail me, so I will reply. like I am traveling on that day, so might not be possible to take. If I get the Wi-Fi, I will take the live session. Okay. Okay then. Thank you guys. Bye.